Distinguished colleagues and guests, I'm Yungang Liu, an AI engineer at TourSynbio. Today, I'm excited to present our latest research achievement, TourSynbio, a multimodal large model and agent framework to bridge text and protein sequences for protein engineering. This work aims to revolutionize the field of protein engineering by combining large language models with specialized protein engineering tools. Let's start with some background. Protein engineering is a complex and crucial field with profound implications for medicine, biotechnology, and materials science. However, traditional protein engineering methods often require extensive expertise and computational resources, limiting their widespread application. Our solution is TourSynbio, the first multimodal large model designed for protein engineering tasks without external protein encoders. TourSynbio is built upon Intel Large Language Model 2.7 and uses protein large model dataset for post-training and instruction fine-tuning. This dataset includes 17.46 billion tokens for self-supervised learning and 893,000 instructions for supervised fine-tuning. What sets TourSynbio apart is its ability to directly understand and process protein sequences as if they were natural language. This approach not only simplifies the workflow, but also improves efficiency. Now, let's look at the performance data of TourSynbio. This table shows a comparison of different protein language models on the protein language model benchmark test. As you can see, TourSynbio achieved a correct rate of 62.18%, the highest among all models, even surpassing larger commercial models like GPT-4 Turbo. Even without post-training, it reached a correct rate of 58.26%, outperforming most other models. In terms of inference time, TourSynbio also performed excellently. The 22.34 minutes inference time demonstrates a good balance of efficiency, especially considering its high correct rate. This result proves TourSynbio's significant advantages in protein sequence understanding tasks. It's not only accurate but also efficient, providing a powerful tool for the field of protein engineering. This performance improvement could lead to faster research progress and new scientific discoveries. Now, let's delve into the fine-tuning process of TourSynbio, which is a key to its success. The fine-tuning process consists of two main stages, post-training and instruction fine-tuning. In the post-training stages, we use 17.46 billion tokens of self-supervised learning data from protein language model dataset. This data is divided into three main categories: Chinese English protein science test pairs, protein sequence English test pairs, and protein-related English tests, as shown in the Table 1. This diverse data composition allows TourSynbio to develop a robust understanding of protein concepts across languages and data formats. The post-training process itself is divided into two phases: initial training on 4K context tests, further training on high-quality 32K tests. This gradual increase in context length enables TourSynbio to effectively capture long-term dependencies in protein sequences. For the instruction fine-tuning stage, we use 893,000 instructions for protein language model dataset, covering various protein engineering tasks and concepts. This enhances TourSynbio's ability to follow complex protein-related instructions and perform specific protein engineering tasks. Throughout the training process, we use consistent hyperparameters as shown in the Table 2. We trained TourSynbio on 8 A100 GPUs, each with 80 GB of memory. This large-scale computational resource allows us to effectively process vast amounts of training data and complex model architectures. Building upon TourSynbio, we developed TourSynbio Agent, a framework designed to execute complex protein engineering tasks. TourSynbio Agent integrates multiple specialized protein engineering tools, offering a conversational user interface. This interface includes four main functional modules: model selection, agent selection, user input, and file upload, as shown below. The workflow of TourSynbio Agent, also as shown below, includes four key steps. Intent classification. TourSynbio analyzes user input to determine if a specific agent needs to be called. Keyword-based agent selection with fuzzy matching. We implement a keyword matching method with independent keyword tables for each agent. Fuzzy matching capabilities are incorporated to accommodate potential spelling errors. User guide selection. For functional similar agents, we implement a selection interface allowing users to manually choose the desired agent. Parameter extraction and interactive validation. We develop customized information extraction methods for each agent using prompt engineering. Agent execution. TourSynbio calls the corresponding agent to execute the task and return the result. TourSynbio Agent integrates various powerful protein engineering tools, including mutation prediction tools like ESM1V and Separate, protein folding and inverse folding tools such as ESS-fold and ESM-if1, protein design and reconstruction tools like AntiFold and Chroma, and visualization tools like PyMore. Now let's look at a concrete example of how TourSynbio Agent simplifies protein engineering tasks. We compare the traditional programming method with the TourSynbio Agent interface for analyzing protein mutation effects. First, let's consider the traditional programming method shown on the left side of the figure. You can see a Python code which looks quite complex. It involves several steps, such as importing necessary libraries, loading the pre-trained models, tokenizing the sequence, calculating mutation effect scores, and interpreting the results. This process requires researchers to have considerable programming skills, familiarities with specific deep learning libraries, and the ability to concurrently set up and use models. For many biologics, especially those without a strong programming background, can be a significant challenge. Now, let's look at how simple it is to use TourSynbio Agent, shown on the right side of the figure. With TourSynbio Agent, the process is simplified to users simply enter a plain language instruction in a dialog box, such as I want to predict the mutation of the sequence. TourSynbio Agent automatically understands this request and calls the tool, in this case the ESM1V model, and the system guides the user through providing necessary information, like the protein sequence and specific mutations, in a conversational manner. And then TourSynbio Agent handles all complex computational process in the background. And finally, the system presents the results in an easy-to-understand format. This approach offers several clear advantages, such as efficiency, error reduction, and flexibility. This comparison clearly demonstrates how TourSynbio Agent significantly simplifies protein engineering tasks, making them more accessible. This not only accelerates the research process, but also allows more researchers to engage in protein engineering work, thus driving the development of the field. To illustrate the practical effectiveness of our system, let me present a case study from our research. Enhancing the catalytic selectivity of the P450 enzyme for steroid compounds. In this case, we focus on the P450 protein that catalyzes the 19-hydroxylation of steroid compounds. The challenge was to increase the selectivity of the enzyme catalyse, aiming for a 70% increase to meeting production scale requirements. Our modification strategy involved two rounds. In the first round, TourSynbio agent recommended 200 single-site mutations within 2 weeks. These were tested in wet experiments over 3 weeks. For the second round, we fine-tuned our business model using the 200 wet experiment data points and recommended 10 mutations with no more than 5 sites. These results were expressive. The correlation between our recommended mutation results and the experimental data reached 70%, indicating high predictive accuracy. Among the 10 recommended results, selectivity was increased by up to 70%, meeting our target. Additionally, enzyme activity was slightly improved. These results essentially meet the requirements for scaling up P450 protein production, paving the way for efficient production of steroid compounds. This case study demonstrates the practical effectiveness of TourSynbio agent in real-world protein engineering tasks. By combining the flexibility of large language models with the precision of specialized protein engineering tools, we've created a powerful platform that can significantly accelerate research and development in this field. Looking ahead, we plan to further enhance TourSynbio's ability to predict complex protein structures and explore the possibility of integrating more advanced structure prediction models into the system. In conclusion, TourSynbio and TourSynbio agent represent a significant step forward in protein engineering, offering researchers a powerful, flexible, and user-friendly platform. We believe that as technology continues to advance, our system will play an increasing important role in driving innovation and development in the field of protein engineering. Thank you for your attention.